Thank you. Thank you very much, Professor Baxant, dear Peter, for inviting me. It's a pleasure for me to be here the second time. I had here a lecture last year about the same time in November. Anyway, I want to introduce myself first. So my name is Mario Hirz. I'm Associate Professor at the Institute of Automotive Engineering at Graz, University of Technology. And in my university, we have a rather long tradition in research in very close cooperation with automotive industry and supplier. So personally, in my department, I have research projects all over the world. So I also teach at a university in Shanghai. I had a winter school last year in Thailand. We had a cooperation with the university. We had a project this year with a startup company in Silicon Valley in San Francisco area. So we are doing our research around the world, and I hope I can give you some impressions of our work in this lecture. Yeah, the lecture itself, it's focused on the transition that we have in automotive industry, so the change in automotive industry. And this transition is mainly driven by three parameters or three influencing factors. The first one is the legislative boundary conditions. I will come to that in a few minutes, very detailed, because this high pressure from legislative side forces the car industry to electrification. So the reduction of emission requires electrification of propulsion system. This is a huge change, a huge transition for the automotive industry. It's a huge investment to change to hybrid or, on the longer term, to electric cars. I will explain that in a few minutes. In the second part of my presentation today, I will talk about automation. Of course, this is a very broad range. So we talk about digital functions in the car, driver support, infotainment, internet in the car. So it would be too long to talk about this today, but I want to focus today on automated driving functions, driver assistance function, automated driving functions, because this is some kind of, let's say, top level of research, what the companies are working on. So these are the two main chapters, and a little bit I will touch the mobility concepts, the business models, but just in context to automated driving cars today. Yeah, let's start with the legislative boundary conditions with a focus on exhaust emissions. And here we can distinguish two types. The first one is the reduction of harmful exhaust emissions of cars with combustion engines. These harmful exhaust emissions are limited very strictly. I have here in the diagram on the right a time frame, and you see the limits get lower for all markets. Is it China? Is it United States? Is it Europe? This is just an example of the nitro-oxygen emissions, but it's the same for particles, for hydrocarbons and others. This problem or this challenge can be solved by technical solutions. So with exhaust gas after-treatment systems. And it's possible to solve that problem. It's possible to reach the target for the industry from side of the technological aspect. A little bit more challenge is the target to reduce CO2 emissions. CO2 emissions are directly connected to the fuel consumptions of cars with combustion engines because we burn hydrocarbons, right? And when we burn hydrocarbons, we produce carbon dioxide and water. And the harmful exhaust emission, but the harmful are less than 1%, so only a small part. And when we have to reduce the CO2 emission, we have to replace the energy carrier because all time when we use here fossil-based fuels, we will produce CO2 and we will put it into the atmosphere, which has a bad impact on the climate effect. You of course know that. And this is the tougher target. So reducing the harmful exhaust emissions we can do technically, also with combustion engines. But reducing CO2, we have to change the propulsion system. So this is the big driver of the change going to electrification. Why is this so on the table, or why is this so important? This is shown in this diagram here. This diagram shows the CO2 emissions of different branches in Europe in the timeline starting from 1990 and until 2018. It's just this diagram. Hello, good evening. And what we see here is from the baseline of 1990, nearly all branches could reduce their CO2 output. So is it agriculture, is it buildings, power generation, industry, waste management? They all could reduce the CO2 output, but not the transportation sector. And that's the reason why the transportation sector is so much in the focus of the European legislation. So here, it has to be done something to reduce the CO2 emission. What is done? Just on the example of the European market, the European Commission defined the so-called Green Deal with the target, or let's say the vision, to have a carbon-free continent in 2050. Across all the branches, right? Zero CO2, it's the vision, let's call it this, in 2050. Now we can say, okay, 2050, it's a long time, I don't care. But we have to care because there are intermediate targets defined. And the next step, the intermediate step, is 2030, a reduction of 50% from 1990. And when we look at this, even if the different branches are good on the way, but they are not at 50%. So that means all over the branches have to work on optimization to reduce CO2 emissions, to reach the 2030 target. And especially the transportation sector has the biggest challenge. Besides this target, the European Commission also defines or proposes technologies. And today I will talk about mobility, right? And on the mobility sector, hello, good evening. On the mobility sector, we have electrification of cars and trucks. This is on the table. We have hydrogen as a fuel. I will talk about this opportunity a little bit later. And we have the synthetic fuels, so carbon neutral fuels, so-called e-fuels. As you see here, there are different applications might be suitable. Electrification is good, suitable for cars, perhaps for trucks in cities, for long-distance cars, for heavy trucks on long-distance. Hydrogen might be an issue. Synthetic fuels is often seen as the solution for aviation, for the airplanes, because they need this high energy density to be able to transport goods or people via air roads. And here, the synthetic fuel is seen as the solution. Besides the transportation sector, also I called it green. Green means low carbon, right? Low carbon electricity production is very important. And for the industry, carbon capture and storage is an approach to take the CO2 emission where they are produced. For example, in steel production, steel industry, where we need very much heat for producing the steel, we should take the CO2 there and do not release it in the atmosphere. We should take it and store it, for example, in deep drawn hills in the earth crust. So this is called carbon capture and storage.
So just for my understanding, I do understand percentage-wise, but transport is not major CO2.
That's a good question. It's this one.
Yeah.
So when we look at your question was regarding how much is the transport, right? This diagram shows the worldwide share. So we have worldwide about 23% of CO2 is produced by the transportation sector. In Europe, it's 28%. So it's a little bit more because we have much transportation in Europe. The other branches are not divided here, but it's agriculture, industry, power generation, and so on. And when we look more detailed onto the transportation sector, we see that about 5% is railway, about 11% is aviation, about 11% is the ships, and 3/4, so about 75% is the road transportation. So the road transportation has a significant impact on the CO2 emission. When we look more accurate, we see that a little bit less than half of road transportation is commercial vehicles, heavy vehicles, and a little bit more than half is the small vehicles, the cars, motorcycles. So when we multiply 23%, multiplied with 74%, we end up with 17% of worldwide CO2 or fossil-based CO2 production. It comes from road transport. And I think this is exactly your question, right?
Thank you.
Yeah. What are the measures of the legislative side? Today I will focus on cars. There are also measures for trucks and other sources or other mobility or transportation devices, but I focus on cars because this is very clear and everybody knows cars, so this is easy to explain. The strategy here is to define fleet emissions. The fleet emissions are defined as an average emission of a vehicle fleet in a market. So for Europe, for example, all cars are counted that are sold and registered in a year, and the average CO2 emission of these cars is limited for the car manufacturer. So the car manufacturers are responsible to reach the fleet emissions. And this is a really tough target for the car manufacturers. I will explain it in a minute in detail. Just to explain the diagram first, we see here the CO2 in grams per kilometer, and here the timeline and different selected markets, United States, Europe, Japan, China. Why did I select these markets? Because these are the largest automotive markets worldwide. So in China, we have China is the largest car market worldwide. About 28 million cars, new cars a year are sold in China. About 22 million new cars are sold in Europe and about 21 in the United States. So these three markets are most significant for the automotive industry in the world. Japan, as showed here, because it's also a large market, and we have innovative car manufacturing in Japan, Toyota, for example. Anyway, what is the status? When we look at today, we have the lowest target in Europe with 95 grams per kilometer CO2 emission. What does it mean? The grams per kilometer CO2 emission are directly proportional to the fuel consumption. 95 grams per kilometer means 4.1 liter gasoline per 100 kilometer or 3.6 liter diesel fuel per 100 kilometer. In average, right? This can be reached by small cars, optimized cars with combustion engine. But when we look at the future target, 2030, we have 59. And here we end up at about 2.5 liter per 100 kilometer, which technically cannot be reached with combustion engines anymore with normal cars. Okay, when we build a very small car for only one person, it could work. But for that, what we understand as cars, it does not work. This means the car manufacturers have to go to electrification. They need to build electric cars to reach that targets. In 2035, it's discussed to go to zero CO2. And here I have to say, perhaps you did read it in the newspapers, there was a big discussion, will the European Commission forbid combustion engines or not? For me, this is just, it's not relevant, because when it's zero CO2, we can operate electric, or we can operate with combustion engines with a fuel that does not have a CO2 impact, right? A e-fuel. I will come to that later. Both can help to reach the CO2 target, of course, if it is the e-fuel or electric car. The challenge here is that the e-fuel will be very expensive. I will show you. Anyway, we see that on the long term that the legislation kicks out combustion engine. So this plan is more or less the end of the combustion engines. Car manufacturers today do not really invest a lot into development of new combustion engines because it does not make sense, at least for the European market. By the way, for the Chinese market, it's very similar. In North America and United States, it's a little bit different. It also depends on political decisions, but in the United States, it also depends a lot on the state. In California, we have very strict boundary conditions. In other states like Texas, not. So it is more diverse. Here I have summarized some facts about this legislation. And in the first line, you see the fee, the payment, the penalty payment that has to be done if a car manufacturer cannot reach the target. And I would like to play a little bit with numbers to give you a feeling. What does it mean? 95 grams CO2, 95 euro per gram violation per car sold in Europe. Let's play with numbers on the example of Volkswagen. Volkswagen Group sells about 3 million new cars in Europe in a year. So this is Volkswagen, Skoda, Audi, Seat, all the cars together. In case that they, in average, exceed the target, let's say 5 grams, not 95, but 100, right? They have to pay 5 grams, multiplied with 95 euro, multiplied with 3 million cars. And this ends up in about 1.5 billion euro for that year. When they cannot reach the target in the next year, they have to pay it again. And 1.5 billion is a lot, even for a car manufacturer. So this is hard to reach for car manufacturer, but they have to reach it because otherwise they have to pay a lot of money. And that's the reason why automotive industry pushes electric cars a lot this time. It's a legislative background that pushes this. Yeah, there are some special regulations like phasing in until 2023. This is now over. Pooling is allowed. So, for example, there was announced in some newspapers that Tesla goes into a cooperation with Fiat Chrysler. And it was not confirmed, but the numbers were told that Fiat Chrysler pays 300 million a year to Tesla, that Tesla is counted in the same pool as Fiat Chrysler, right? So it's a good business for electric car manufacturer. Yeah, there are some reliefs for very small car manufacturers, sports cars, Ferrari, or others. What is the result of this legislative pressure? At the short term, so let's say in the next 4 or 5 years, we see clear optimization of combustion engines. Also smaller combustion engines. So the large combustion engines with 6-cylinder, 8-cylinder, they die out. Or they might be offered, but only in very small scale production. We have 4-cylinder engines, 3-cylinder engines, because they have a lower fuel consumption. And of course, electrification. So HEV means hybrid electric cars, plug-in HEV, also PHEV, plug-in hybrid electric cars, and BEV means battery electric cars. So all the car manufacturers invest in electrification, and I will talk about that in a few minutes more detail. On the long term, so when we look at 2030 plus, it's very clear that it goes into electric cars. At least at the European market, I showed you before the diagram, there is no way out, so the electric cars will take over, and car manufacturers take some time to change their product portfolio, right? So, for my opinion, most of the car manufacturers will have ready their electric car fleets in about 2030, and the combustion engine cars will fade out until 2035. This is reasonable because of production volume, because of economic reasons. Then we have hydrogen vehicles. I will come to that in a few minutes more detailed. And we have the synthetic fuel. I also talked about that. I see those more in niches, so not so much in the average car on the road.
If I can, I do not exactly understand the difference between China regulation and Euro. Just maybe crazy comparison. You can buy, I would expect that China regulation is much tougher because you can buy ID3 from Volkswagen in China for like 400,000 Czech crowns.
That's right.
If you will buy it here in Europe, you will pay 1.2 million.
Yeah, that's right. Yeah, thank you for the question. There are different aspects to be considered. The one is the economic one. The Chinese market is a very tough market for electric cars today because there are Chinese car manufacturers that offer cars for that price. And so Volkswagen was forced to reduce the price for the ID.3 to that value. But they reduced the comfort of the car. So they did equip it different. But in general, you're right, the car is much cheaper there than in Europe. This is the economic side. So the competition of electric cars in China is very hard for European manufacturers. Also for Mercedes-Benz. Perhaps you did hear that Mercedes-Benz released the EQS, so the electric S-Class in China. And after they released, they had to drop the price. About it was 30% or something like that.
And the margin is supposed to be about 7% or something like that, so they are losing money.
That's the point. That's the point. So it's a very difficult market, but it is a very important market because the Chinese market is growing. So traditional or Western or perhaps German car manufacturers struggle in China, but they have to find their way to be competitive there.
Yeah, they need to earn money from our pockets.
Yeah. Perhaps for a certain time, for a certain duration. Also, Tesla dropped the price, not only in China. Tesla seems to run well, right? And the second part of your question was about the Chinese legislation. Yeah. And here, we have a different situation than in Europe. Because in China, we have different provinces, different districts that can define their own legislation in terms of electrification. So for example, in Shanghai, you pay about $10,000, counted dollar, when you want to register a new car with combustion engine. It's really expensive. When you buy an electric car and register that, you just pay $1,000. So this is a measure that the Shanghai government takes to push the customers to electric cars. And there are some other incentives of electric cars in different cities, but it's more regional. So for total China, they do not forbid combustion engine because China is very large and they know they don't have the infrastructure for electric cars. So they need still combustion engine cars, but in cities with bad air quality, with problems in terms of traffic, they want to push electric cars. So it's more diverse than the European legislation. Okay. But thank you for your question. Yeah, let's have a look into propulsion technologies. It becomes now a little bit more technically. Here, just on a nutshell, I will not go into detail too much, but just to compare what do we have as propulsion technologies. Combustion engines, it's a traditional or the well-known technology that we have. It works very well, it's very cheap. So just to give you a value, a modern combustion engine, ready to be built into a car, a gasoline standard engine costs about 1,000 or 1,200 euro. That's the production price of a combustion. It's not expensive. Of course, I have the fuel system and exhaust system and so on, but it's a relatively cheap technology, especially in comparison to electric drives. It works well. It has some potential for improvement, but this is limited because, and here we come to the disadvantages, we have a thermodynamically limited efficiency. From the combustion process, we cannot improve a lot. This is the so-called Carnot process. Perhaps the mechanical engineers of you know that. The Carnot process is a simplified process that represents the combustion process in an engine. And this process is driven by the upper and the lower temperature in the combustion chamber. And we cannot really extend here a lot. The lower temperature is the temperature of aspirated air, right? In winter, it's lower than in summer. And the upper temperature is the fire or combustion temperature in the chamber, and this is limited by the materials. We cannot extend it because the piston would melt. In this way, the theoretical process of a combustion engine, the Carnot process, reaches an efficiency of about, let's say, 75% in theory. But now we have the losses, friction, heat losses, combustion losses, losses through the exhaust system, and so on and so on. So that in real combustion engines, we have best efficiency of about 43% in diesel engines for cars, and about 35–36% in gasoline automotive engines.
And one pump that is being used now as charger?
Yeah, the Wankel has a worse efficiency because it has a lower compression ratio, but it's very compact, and therefore Mazda uses it. It's in brand new in a car in a serial hybrid as a charger. That's right, but it's more because of packaging, because it's very compact, not because of the good efficiency.
Okay.
Electric drives reach efficiency in the area of 65–70%. So it's double or even more than a combustion engine. And that over a very wide range of usage. So at part load, at high load, I have a diagram about that later. Electric drive is comfort, is quiet. But with the electric drive, we have the very expensive battery system. I will show you on one of the next slides. So we can estimate today about 35–50% of the production cost of the car is the battery only. And this has a high impact, right? Also, the battery has an impact on the CO2 emissions. I have also a diagram about that. And very important, with electric cars, it depends on how the electricity is produced. I also have a diagram about this. So we need to have low CO2 electricity to make the electric car a low CO2 use, right? The hybrids finally show a combination of electric car and combustion engine driven car. And it's not a bad idea because we can take the advantages of the electric drivetrain, the advantages of the combustion engine drivetrain, but it's not a zero emission technology. So it's just a support on the transition on the way. And there are different types of hybrid, full hybrid, mild hybrid, plug-in hybrid, so a broad variation. At the end, the hybrid CO2 reduction potential of hybrid drives is also significantly influenced by the user pattern. So how the car is used. Is it used on the highway for long distance? Then it does not make a big sense. Is it used in city traffic with stop and go? Then it has a better effect on CO2 reduction. Yeah, here just some theory. I will be very quickly here, not too much detail, but on the upper line, you see different types of hybrids. So we have serial hybrids where the combustion engine drives a generator and the car is driven by electric motor. This was the example of the Mazda Wankel. There is another example on the market from Nissan, which is also a serial hybrid. So the car, in fact, is driven by electric motor. The combustion engine only charges the battery. Then we have the parallel hybrid with different configurations. The parallel hybrid are mostly used by traditional car manufacturers because they integrate the electric motor into the existing powertrain. And this is low investment, so it's relatively easy to do that. And it's very effective, for sure. There are different configurations which are defined by the place where the electric motor is placed. And the last one is the so-called power split or combined hybrid. It's more or less the Toyota system that Toyota introduced with the Prius more than 20 years ago, where we have a so-called power split device. It's a planetary gear that combines combustion engine and electric motors, and that switches very quickly between the operating modes to always find the optimal operating mode. So with a good configuration, a hybrid can reach a fuel consumption of about 25% in comparison to a standard car. On the lower side, we have the electric drivetrain, where we have the electric energy storage. It's a high voltage battery, typically 400 volt. Some car manufacturers use 800 volt to reduce the losses in the system. Then we have the electric motors. Here we use a permanent magnet synchronous machine or externally excited synchronous machines, or as an alternative we use induction machines. Both is used, both are three-phase, in most cases three-phase alternating current machines. And the link between the direct current side of the battery and the alternating current side of the electric motor, the link between is the inverter which has the task to convert the direct current into three-phase alternating current when driving the car. But when braking the car, recuperation, so electric braking, then it converts the other way around to charge the battery. This is also a rather sophisticated component because it has to provide very high power conversion, right, at a high frequency over lifetime. So the efficiency should be good, the lifetime should be good, the cost should be reasonable. Yeah, and then we have a transmission which is typically very simple. Most of the electric cars just have a rigid transmission here, not shiftable. Just some sports cars have a double clutch transmission, but it's a very simple transmission here. When we look at the characteristics, so let's compare a combustion engine and electric drive in a very rough overview. We see on the upper line, we see the delivery diagram of a combustion engine, right? So we see here the torque and the power over the engine speed. And as we know, with the combustion engine, we have an idle speed. A combustion engine does not work at 0 speed, so we have an idle speed. And then we have a limited maximum speed. It depends on the technology of combustion engine, 5,000, 6,000, perhaps it's a sports engine with 9,000 RPM, but it's limited. And due to that, or because of that limited speed range, we need a gearbox, right, to shift the gears. And in addition, because at 0 speed it doesn't work, we need, for start driving, we need a clutch. And the clutch is a friction element, right, that overbridges the speed difference. That means every time when we start driving, we release the clutch, we produce friction, and we produce losses. Also, when we shift the gears, we produce losses, right, because we have a speed difference in the gear, and we shift that, we activate the clutch, and we produce losses. This behavior we do not have with electric motors. Electric motor produces a high torque at 0 speed. On the upper side, we see the motor, on the lower side, the generator. It's just to show that we can use the same electric motor for braking the car and produce electricity to so-called recuperation, so to charge the battery. And here we see the very nice behavior of electric motor. High torque at 0 speed, so we need no clutch, we need no gearbox, because we start driving at 0 speed. Then we have a high torque level until the so-called field weakening point. The electrical engineers know that very well here. Then we have the field weakening area, and then the torque behavior up to a maximum speed. In this example, I have 12,000 RPM, but there are other electric cars with more than 20,000 RPM speed, so it depends on the technology. This characteristic is very helpful for driving. So when you already have tested the electric car, you can feel that. When you push the gas pedal, which is not the gas pedal anymore in an electric car, right? It's an electrical pedal. You feel the acceleration. It's very good from standing on, and very smooth, and no interruption when gear shift and that stuff. So just on this side, considering this here, the electric motor is much more suitable for propulsion than the combustion engine. And the other side of the diagram here, or of the slide, you can see the efficiency behavior. And the green, so on the upper side, we see a typical efficiency diagram of a combustion engine. We see again the torque and the speed, and we see here in the best area, this combustion engine has 35% efficiency. So it's a modern gasoline engine, for example. But what we see is that this optimal efficiency area is very small. So it's just here in the upper area. When we go more down in the load, we go down to 27, 25, or even less. And now comes the weakness. In daily driving, when we operate the car, we do not operate in full load. It would cost a lot of money by the police, right, to drive too fast. So we operate the car here in this area where the efficiency is not optimal. That means in real driving, we have an additional drawback of the combustion engine drivetrain, that we cannot make use of the good efficiency area. With the electric motor, it's different. At the first, the electric motor has a much higher efficiency range. So in modern electric motors, in the best area, 95, 94, 96% is is done in mass production. And at the second, we see that the area of good efficiency is huge. Nearly the entire operating map, we have a good efficiency. So when we do daily driving here, we have very good efficiency. And this also speaks for the electric motor. So from the technical side, from side of the motors, the electric motor has significant advantages in comparison with the combustion engine. Of course, not shown here, and I will discuss later, is the battery. Because of the energy storage capability that is limited with the battery, I will come to that in a few minutes. Here, another aspect when comparing combustion engine drive and electric drive. As you see here at the left, a very simplified powertrain with internal combustion engine, ICE. In total, just to give you a number, a powertrain with internal combustion engine has about 1,200 parts, a standard powertrain. This is the combustion engine with the valve train, the piston, conrod, the housings, the shafts, the bearings. It's the gearbox, it's the fuel system, the tank system, and so on. In comparison to that, a powertrain of an electric car has about 300, perhaps 350 parts. So a significant lower number of parts. That means a lower complexity on the mechanical side. This means lower effort for maintenance and service. You don't need an oil change here. You don't have shiftable gears. You don't need oil filter or air filter change or that stuff. You don't need that at electric car. But you have the battery. And the battery is a very complex and very expensive electrochemical system, which has its own challenges in terms of safety, in terms of weight, in terms of costs. I will come to that later more detailed. Here, finally, my final slide in this section, what's about the costs? A colleague of mine supervises a master thesis of Mr. König at the Technical University München. And Mr. König has analyzed the production costs of car with combustion engine and a battery electric car. Just to give you an idea, this is of the size of the Volkswagen Tiguan. So it's a compact SUV, right? And Mr. König analyzed it very accurately. So he showed here the production costs for the engine, combustion engine, for the drivetrain, it's a transmission, for the interior, exterior, for the bodywork, all the main components in the car. And when we compare this with a battery electric car of the same size about, we see the price, the production cost is about half higher, right? About 50% higher. And the main share is the battery. So we see here the battery alone is nearly half of the production cost of the electric car. This is because of the very high energy demand of battery cell production, the materials demand. We have expensive materials in the battery cells, and also in terms of the assembling and the manufacturing of the battery itself. Mr. König then did also go have a look into the future. So just to have a perspective vision, what's in about 8 years, 7 years. And here he estimates a drop of manufacturing cost of the battery to the half because of volume effects, but also because of other materials. So we talk here about lithium iron phosphate or natrium iron, so sodium iron batteries, so alternative materials which make the production of the batteries cheaper. And at the end, it's just about 10% difference that we have here, right?
Do you have any details behind economical calculation? Because I'm surprised that in 10 years we are saying that costs will be higher only like 1%. You see 14,000 and 14.6. Mm-hmm. What I see as not cost on cost side, but on sales side, it's going totally crazy. It's like 40% plus.
Yeah.
So I just don't understand.
Yeah. The combustion engine will be moderately more expensive because of increased exhaust emission legislation, mainly.
That's
yeah.
part of it, but
yeah.
I do not see it here. Because
yeah.
it was free before, and 10 years later it's still free.
I have to say that this does not include the loss of money. So it's calculated from the perspective of today, and of course the loss of money has to be added here. But to enable a direct comparison, because we cannot estimate the value of money in 2030, there are other effects. But purely from technical side, it's a very low increase, because the car manufacturer switched to gasoline engines. The diesel production will be reduced because of the high effort for exhaust gas after treatment. And in the gasoline-driven car, there is not much more effort to reach the emission targets, only in the combustion engine. Yep. And that's the reason for that numbers. Yeah. Okay, yeah, let's continue. I talked about the different types of powertrains, and now let's look at the impact of CO2 emissions of the entire car, not only of that what happens in the car. And this is a very important slide to show that, because we do not have only what happens in the car, we also have to consider how is the energy provided or produced. In case of a car with combustion engine, we burn the fuel in the car, right? So this produces CO2 emissions. In case of an electric car, we don't have an exhaust, so we have zero CO2 in the car. But we have it upstream. We have it before, because we have to produce the electricity. In case of a car with combustion engine, we have to produce the fuel. That means the oil production, refining process, transport, bringing that into the gasoline gas station. In average, just to give you an idea, the share of this preparation is about 10 to 15% of the CO2 emission produced in the car. It might be even a little bit higher. It depends on the oil quality and processes and so on. In case of the electric car, we have to consider how electricity is produced. And this share is called well-to-tank. So the preparation of the fuel or the energy for charging the car or fueling the car. What happens in the car is called tank-to-wheel, from the tank to the wheel. So to sum it up, for the car with combustion engine, we have the tank-to-wheel emission because we burn the fuel in the car, plus the well-to-tank emission, which amount to about 10 to 15% plus to consider the preparation of the fuel. For the electric car, we have zero tank-to-wheel, but we have the well-to-tank emission. And the well-to-tank emission are a function of the technology of electricity production, right? Here, on this slide, you see this impact of electricity production. So you see here the gram CO2 produced per kilowatt hour electricity. It is CO2 equivalent emission. That means different factors are converted into the greenhouse gas effect. And what we see here, the coal power, we have about 1,000 grams per kilowatt hour. So this is worse in terms of climate change. We have the oil power plants. They are not so much seen in Europe, but we have the natural gas power plants, which are very popular in Europe, which is about the half of the coal, but which is still about 450 grams CO2 per kilowatt hour electricity produced. And then we have different types of so-called renewable energy sources. It's the hydropower, it's the solar power, the wood chips, biogas, whatever. And you see it's very low. It's not zero because they have to consider the building of the power plant, service of the power plant, and so on, but it's very low. Also, nuclear power is, in terms of CO2, very low. So CO2 impact of nuclear power is very low, but not shown here is the costs. Nuclear power is relatively expensive, and nuclear power has some risks. You all know them. Also with the disposing of the nuclear waste, for example, what should we do with them, and so on and so on. But this is not shown on this diagram. This diagram just focuses on the CO2 emission. Now, more important is to consider the mix of electricity production in a certain area, in a country or in a region. And when we look at this, I have here on this diagram two axes or two dimensions shown. The one is the average electricity mix in a country or in a region, CO2 equivalents in grams per kilowatt hour. This considers that in a country we have some water power, some coal power, some wind, and so on. So the mix is considered here. And here we see the impact. So how much electricity is produced in the market. And when we look at this, we see that China has a very big impact because it has, on the one hand, it is the largest electricity producer in the world by far, with about 7,000 terawatt hours per year. And due to the high share of coal power, it also has a high impact on that.
Is this as of 2022?
This is 2022, correct. I have to say that China is the largest investor worldwide in reducing the CO2 impact, right? They invest in solar power, in wind power, also in nuclear power, I have to say, but they are working on that, and a small lowering of the footprint has a big result, right? Then I have United States here, I have the European 27, and I have selected countries here. So I don't have the Czech Republic. Norway is very low. They have water power mainly. France is also very low, but France has nuclear power, 75%, right? And there are some other countries, so you can watch out. Germany, for example, with about 400. Germany even tends to increase because they closed the nuclear power plants. Poland with a relatively high share of coal power. India with a high share of coal power. So here, different regions, different areas. And here I would like to show you a web page, just for your information. It's electricity map. You see the link here? Do we have internet access?
No.
No, okay. So I'm sorry I cannot show you here, but you can try it. When you look for electricity map, they show the CO2 footprint in real time in different countries. And you also can see how electricity is produced there, right?
It is also available like application for a mobile phone, and you can see on it on a real time.
This is correct. There is a mobile phone app. It's for free. It's not the only platform, but it's very nicely represented here. Okay, and now let's do a calculation. Do we have a pen? Or otherwise, I will write on the screen.
You have paper. You can use the board.
Can I use the board?
Yeah.
Okay.
There is minimally a red pen.
Red pen is fine. I just want to give you some numbers. Wonderful. Thank you. Thank you very much. I just want to give you some numbers, and now I would like to compare a diesel car and the electric car, right? Let's say the diesel car, I will write big so that you can read it there. When I have the diesel car, what can we estimate as a fuel consumption of a diesel car? Give me a number. 5 liter. 5 liter per 100 kilometer, right? And when we calculate here now the tank-to-wheel emissions, so what happens in the tank, we can calculate them by using a very simple factor. The factor for diesel I've written down is 26.2. For gasoline, it's a little bit lower because gasoline has a little bit different hydrogen and carbon constitution in the fuel. So for diesel, we calculate here 5 liter multiplied with 26.2, and this equals to 131 grams per kilometer. Gram CO2 per kilometer. Now we have to add the well to tank, right? well to tank, and we add about 15%. So just for simple estimation, plus 15% equals to, now please, do you have a calculator or a smartphone? What is 15% of 121? It's about 20, right? 131? 20.6. Thank you. So it's 20.6 grams per kilometer, so that in sum, we have about 152 grams per kilometer. This is our CO2 footprint of a diesel car, right? As you see, we are far away from the 95, right? Even with a 5 liter, and 5 liter is a good diesel car, an efficient one. What about the electric car?
It's tricky. It's very tricky.
When we have the electric car, and here we have to assume an energy consumption of an electric car. So I came up from Graz here today with a Tesla Model 3, pardon, and my wife was driving a little bit fast on the highway, so I had an energy consumption of nearly 20 kilowatt hours per 100 kilometer. It can also be lower, but let's take the 20, it makes the calculation simple. 20 kilowatt hours per 100 kilometer, and now I have to look at the electricity mix. And I charged the car here in Czech Republic, and I would like to know the electricity mix of Czech Republic today. Pietro, do you have the app?
Yeah, I have. It's about 543 grams actually, but I don't know what is let's say 24 hours.
Yeah, 24 hours is good.
605 grams.
600. Let's take 600. 600 grams per kilowatt hour. And out of that, it follows when we have 20 kilowatt hour per 100 kilometer, so it's 0.2 kilowatt hour per kilometer, and we have 600 gram per kilowatt hour, we can calculate that to 120 grams per kilowatt hour CO2, right? And this is with a relatively high CO2 impact. We have 600. If we would charge the car in Norway, just to play a little bit with numbers, right?
Say in Austria,
Oh.
it's 243.
In Austria, we have 243 grams per kilowatt hour. That means we have about 48 grams per kilometer. Right? And this is pretty low. Or when we can go very low to Norway, or if you...
Norway is just only 25.
25. Or you charge it with a solar cell, right? With a solar production. We have here 25 grams per kilowatt hour, and this leads to 5 grams per kilometer. What I wanted to show you with this example is how electricity is produced defines the sustainability or the low CO2 footprint of electric car. And the differences are huge. But even when we drive it with a certain share of coal power, which we have here in Czech Republic today because of the weather we have today, we are much lower than the diesel car, 120 versus 150 grams per kilowatt hour.
We are in academic soil, so let me be a little bit picky.
Mm-hmm.
With electric cars, it's not only consumption. Charging is the key. You can have charging losses, like 10%.
Yes.
You can have charging losses like 15%.
Yeah.
And you can have charging losses like 30%.
Yeah, that's right. Here it depends on how much power did you charge. When you do slow charging with low power, you have very low charging losses.
Not exactly. If you have wrong electric car, where producer is
I talk about good electric cars.
Okay.
Yeah, I talk about good electric. So when you have state-of-the-art electric cars, you can estimate charging losses of about 3%, 5% with low power charging. We have measured that. When you go to high power charging, but also good electric cars, so modern electric cars with 100 kilowatt charging power, 150 kilowatt charging power, the losses are in the range of 10 to 15%. When you go even higher, so Tesla supercharger at the peak 250, you can reach more than 20%, up to 25%, but this is only short term because the power is reduced due to the heat development. So, but it is an impact, that's clear. For the 20%, I have added the charging losses because we have seen it on the screen, I think 18 or 19, 18 point whatever for driving. And here I have added also to make the number more even for calculation, but it's absolutely right. And another aspect that also has to be considered is the production of the car, right? And this makes a big difference. I want to point out this factor. So what we have calculated here and what I have talked about up to now was using the car, right? Using the combustion engine car or the electric car. But we also have to produce the car. And this production of the car is considered by the so-called life cycle assessment. In the life cycle assessment, we consider more or less 3 phases. The one is the production of the car, so the CO2 equivalent emission when producing the car. This also includes the material provision, the transport, assembly, all the processes. Then we have the use phase. This is the well-to-wheel consideration. And we have the end of life, the recycling phase. Today, the recycling of the electric cars is very difficult to calculate on large industrial level because there are not so many electric cars to be recycled yet. This will change in some years, and then battery recycling will be in place. Battery recycling will enable to take back a certain share of material to bring it back into the cycle. But it's not really on a large industrial scale, so I did not consider it very much here in this. But just to show you, what you see here is what is considered. When we do a life cycle assessment, we have energy and natural resources. Out of that, we produce materials for the car. It's the steel, aluminum, it's valuable materials for the battery, for electric motor, also for combustion engine, it's plastic, all that stuff. Then we produce the car, and this too is vehicle production, right? Then we have the use phase, as shown here. It considers the well-to-tank and tank-to-wheel emission. It considers maintenance and service, replacement of spare parts, also the driving mileage and how the car is driven. So the user, is it a very careful driver or is it a sportive driver, for example? And finally, the end of life with disassembling, with recycling, with waste management. In a rough estimation or in a general diagram, when you compare similar cars, so same size, same comfort level, we can see that the production, and this is only the production, of battery electric cars has about 50 to 100% higher CO2 impact than the production of a combustion engine driven car. The hybrid car is somewhere in the middle, and here it depends. If it is a mild hybrid, it's nearly the same with combustion engine car. If it is a plug-in hybrid, it can be up to be 50% higher because of the battery. So this is the range where we operate, and what I would like to show you is an actual example that we have calculated. So we have done this in a project where we have compared 3 cars in mass production, 3 available cars. The first one with combustion engine, it was a compact car class. So the car with combustion engine was similar like a BMW 1 Series with combustion engine, right? Then we have a hybrid electric car. It was similar like a Toyota Prius. And the electric car was similar to a Volkswagen ID.3, so a compact electric car. And we calculate here very accurately the production. This considered the country of vehicle manufacturing, the country of battery manufacturing. This was important because of the electricity mix of the cells which are delivered from China had to be considered here. And we ended up in about 7.5 tons CO2 for the car with combustion engine. About 9 tons CO2 for the car with hybrid drive, and about 14 tons CO2, so nearly double of the car with combustion engine of the car with electric motor and electric drive. And this was the impact of production. And now we can look at a completely life cycle, right? And this I would like to do by use of this diagram. In this diagram, you see the life cycle CO2 impact of the different cars, and we estimated 200,000 kilometers. So it might be more. We estimated 200,000. And here you see the tons CO2. This is the car with combustion engine, where we have the 7.5 tons of production here. And then, due to the usage of the car, we burn the fuel. We have an increase of up to 40 tons over 200,000 kilometers. Also considered here is the wear parts and spare parts, but the share is very small of that. When we look at a hybrid car, it has a higher impact of production, 9 tons, but a lower fuel consumption, about 25% lower fuel consumption. So the total CO2 impact is considerably lower. It's nearly 20% lower, right? And now we look at the electric car. With the electric car, it depends on how it is charged. We have here the 14 tons in production, so really high impact. But when we charge the electric car with low CO2 electricity, I've just written it down here, the Norway mix as an example with 25 grams per kilowatt hour, but it could also be solar energy here in Czech Republic or hydropower here in Czech Republic, then we have a very low total impact of 16 tons. When we charge the electric car with a high share of coal power, just as a visualization, representative, the mix of Poland, the average mix over a year of Poland, we end up in a higher footprint than the combustion engine driven car. And here in between, you can calculate it by yourself with these equations I have shown you, right? So I have different countries here in between. In Germany, for example, 30 tons. In European average, 26 tons, and so on. So here, this gives a big or an idea of the big impact of electricity production. Please.
There is one little bit small, it's not mistake, it's not point of view. If you look how is charged the electric cars, its owners usually have a photovoltaics, or much often than people who use it internal combustion cars. So in reality, this line will be a little bit more splitter even in Poland.
Yeah.
Because the customers are using more electricity from photovoltaics.
I agree. So I don't want to punish Poland here. It's just as representative. And of course, when you use a solar cell, you are at the level of Norway. Absolutely right. What I show here is just the average mix, and I agree, of course, it depends on. In Austria, for example, we have the possibility to purchase Ökostrom, which is electricity only from water power, wind power, and solar power. So when I have a contract with an Ökostrom supplier, I only have green electricity. Absolutely right. But at the end, in a country, electricity is used. And if you use a higher share of Ökostrom for electric car charging, the coal power will be used for something else. So at the end, it is always the average mix that has an impact on the atmosphere or on the climate warming. That is more or less the say here. Yeah, and out of that, we just can calculate some break-even points. So for example, when we compare the combustion engine driven car and we charge it with low carbon electricity, the break-even point is below 50,000 kilometers, right? So it makes sense, absolutely. Okay, yeah, so far to this, perhaps a short sidestep to alternative fuels. I don't know what's the time.
1 hour.
It's about, okay, so I will be quickly.
So I think 40 minutes.
Yeah.
But it
Okay.
depends on you.
Otherwise, you have to give me a warning.
On the auditorium.
Typically, I talk endless and I have to be stopped. So just give me a sign. Anyway, what about hydrogen? Hydrogen is a very attractive approach for storing energy. When I went to school 100 years ago, I learned in school hydrogen is the fuel of the future, right? Then I did study at the university, and as a student, I learned hydrogen is the fuel of the future. And today, I tell my students, hydrogen is the fuel of the future. You see the joke in the story, right? Since decades, hydrogen is the fuel of the future. But why? And the background is it's a very nice possibility to store energy in a cyclic process. So we can produce hydrogen with green energy by electrolytic conversion of water. We can store hydrogen. This is more or less solved in high pressure tanks in cars. We can convert hydrogen into electrical or mechanical energy in fuel cells, or we can do it in combustion engines, drive a car. And what comes out is water, which we can use for producing hydrogen again. So it's smart, isn't it?
It makes perfect sense, but economically it is a disaster.
It's expensive.
It's a disaster. It's
Yeah, I will come to that point. I agree, it's expensive. I don't want to use disaster. I don't want to use the word disaster, but I will come to that point. But what are the let's don't say disaster. I don't want to say disaster. I saw challenges, right? I'm an engineer. Disaster is when it explodes, but to solve a problem is a challenge. But the challenge, the biggest challenge in this cycle today is that hydrogen is produced from natural gas. That is the status of the art. 95% of all hydrogen that we use on Earth is produced from natural gas. And this is, it's not a bad idea, because natural gas, it's mainly CH4, so it's methane, right? And when we look at methane, we have 4 atoms of hydrogen and 1 carbon. It's a good idea to split up natural gas and to produce hydrogen. The disadvantage is that the carbon goes into CO2. So when we produce hydrogen from natural gas, it's not green. There is a certain CO2 impact. And this is the problem. As I said, 95%. So when you see some research vehicles, green hydrogen on it, you have to ask where does the hydrogen come from. In most cases, it's not green. And this is the problem. So hydrogen, it can contribute a lot, but at first we have to make sure that it is produced not from fossil sources. Out of my experience, or what we do in research, is to use hydrogen for energy storage because of the high fluctuation of sustainable energy sources. So when we have the version of going to 0 CO2, Green Deal, I started with that in my lecture today, we need solar energy, right? We need wind energy, we need water energy, low CO2 impact, but in the night there is no solar energy. If there is no wind, we have no wind energy. On the other hand, if there is a storm, we have a very high wind energy. And we have to store this energy to compensate the low producing areas. So in that way, we need technologies to store these high fluctuating natural energy sources. It's wind, it's solar, also water. And what can we do? How can we store electricity in a large scale? Do we have some ideas? What is done today?
There are petrified gas, but economically they are not working. You can use energy and store it into chemical substances.
Yeah.
Personally, I guess that ammoniac maybe is not the worst idea, because you can use it in our existing
but what is done today? What is state of the art? How do we store fluctuating electricity production?
Technology-wise, you can use electricity and you can use hydrogen using electricity and water.
Yeah, but it's not done on large scale. Today, we have pump power plants, right? Where we pump the water up to the mountain and we release it down. It works very good, but you need mountains, right? What else can we do? Chemical energy, you mentioned it. We can convert electricity to hydrogen. It's not done on the large scale, but it can be done. Or if we can use ammoniac, sure. So chemical energy. Also e-fuels, I will come to that on the next slide, is a possibility to store energy from high fluctuating sources. What else can we do? Battery systems. But on the really large scale, battery systems are pretty expensive. So there are some projects in Australia, for example, or in Germany, they opened, but it was, I think, 250 megawatt hour, something like that. It's huge, but it's only tiny in comparison to the entire electricity production. So battery is expensive. What else can we do? There's not much, right?
What about kinetic energy storage?
Kinetic, yeah, or geodetic storage. So in China, they built some kind of elevator. They lift up a very heavy concrete block and they let it down to produce. So there are some ideas. But as you see in the discussion, it's not really easy to do that. Another possibility is to do it decentral, to use electric cars with bidirectional charging and discharging function as intermediate energy storage, right? And when you do that in a city where you have thousands of electric cars, you can manage that. So that also is an approach for the future. But I just want to point with this discussion, it's not so easy to store electricity from renewable sources on a large scale, and hydrogen can play a role here, but we have to do it. It's not done yet enough or not done yet on a large scale. Yeah, these are just some numbers from the hydrogen car. I just want to jump on the e-fuels before I finish this chapter. With e-fuels, it's also a chemical energy storage. We have from the history different technologies, biofuel, for example, with ethanol in Brazil, it works, or gas to liquid, power to liquid. But the technology I want to point out is the so-called e-fuel, the power to liquid. Because this is much in discussion today. The idea is to take out CO2 from the atmosphere or from CO2 sources like the industry, to synthesize this with hydrogen and to produce hydrocarbons. So we take CO2 plus hydrogen and produce hydrocarbons. This works. The drawback is we need a lot of energy for that. But there are some prototype power plants. Perhaps you have heard from the project from Siemens and Porsche. They do that in South America because there is much wind there. And they have installed a windmill there that produces electricity. And it's still in work. So they take out CO2 from the atmosphere. They synthesize it with hydrogen. And they produce e-fuels. Here are just some numbers that you get an idea. For 1 liter e-fuel, we need 3 liter water, about 6,000 cubic meter air for CO2 extraction, and about 16 or even more kilowatt hours electricity to produce 1 liter e-fuel that has an energy content of about 8.5 kilowatt hours. So it's high effort, but it works. And this could be one solution to produce e-fuels or hydrogen or both in a region where we have high natural energy like wind or solar energy, and then to fill it into tanks and to transport it to Europe to use it here, or to use it in airplanes. So this is the approach of the e-fuels.
Just to highlight, we consume 16 kilowatt hours, and we end up with 1 liter of a fuel that contains 8.5.
Yes.
So we have losses like half.
Yes, this is right. And I have to say this 16 kilowatt hours was published by Siemens. So I did not, cannot confirm it. I estimated it's even a little bit higher. Yeah, that's right, yeah. Yeah, and now for the last slide of this section of powertrains of the future, I would like to compare the electric car, the hydrogen fuel cell car, and the combustion engine driven car. And I would like to compare it under consideration of the vision 2050. All three technologies should operate with zero CO2 or near zero CO2. So we are in this vision of the Green Deal. How does it look like? And this diagram was published by Transportation and Environment, but I more or less agree with the numbers. They're a little bit positive for electric car, but in general it shows very nicely what we look here is the efficiency. And the efficiency can be taken as an indicator for the price, for the costs. When we have the electric car, we have the green electricity. This is the basis. We charge it with the electric car. We have some kind of losses for spreading for the infrastructure. We have some charging system losses, some battery losses. Here estimated very low. We discussed that before. Then we have some losses in the electric motor, in the inverter. So it ends up to about, this is a little bit positive, I would say 65 to 77% in this range. This is the efficiency of electric powertrain with green energy, considering well to tank and tank to wheel. When we look at the hydrogen fuel cell electric vehicle, and we assume we are in the future, we produce the hydrogen from electricity. So we have here the electrolytic conversion, about 78% efficiency, 22% losses. Then we have to compress the hydrogen. As I told before, 700 bars is a high energy demand for compression and transport of the hydrogen. So we end up to about 60% to tank. And then in the car, we have the fuel cell to produce electricity. Here it's estimated a little bit more than 50% efficiency, so 46% losses. Inverter electric motor, that it ends up to about 30%. It's not a bad value. I can believe that, about 30% total efficiency. That means when we drive 100 kilometers with an electric car and 100 kilometers with a car with a hydrogen fuel cell, the costs will be double about here, right? Because half efficiency, we need double energy. What's about the combustion engine? So here, we produce e-fuel. So CO2 neutral fuel. We at first produce the hydrogen. Then we take out the CO2 from the atmosphere. We synthesize so that we have total about a little bit less than 50% efficiency. This was also the energy calculation we did before. And in the car, we have the combustion engine, which let's say average 30% efficiency, so 70% losses, so that we have about 13% total efficiency. That means 4 to 5 times more expensive than the electric car. And here I come to the end of this chapter because of this consideration I talked about in the beginning. E-fuels are a solution, yes, to contribute, but they will not be cheap, right? So when we do that, there will be a certain increase of cost factor. Therefore, I think that for cars, electric cars have the greatest opportunity. There might be some other technologies for trucks, for example, for airplanes and others, but for cars, I believe that e-fuels are relatively expensive. On the other hand, e-fuels provide the possibility to be filled in the existing car fleet, so the cars that we drive today on the road. And we should apply measures very quickly to reduce the climate change. And it would take a long time to change every car to electric. In the meantime, we can add e-fuels to the fossil-based fuel to reduce the footprint of the existing car fleet. Please.
I have a question. You think I will put to current fleet cars? My question is, how long is usually life of the car?
Yeah. I know it for Austria and Germany, average life is about 12 years. but then the cars are exported most out of Europe. But when looking at Europe, we have about 12 years. That means when the reduction of sales of cars with combustion engine gets significant in 2030, it might be, then we have these cars 12 years on the market, 2042, right? Or even longer. And for that time frame, e-fuels can make sense to reduce the fleet emission, because 2042 is a long time and too much CO2 brought into the atmosphere. Yeah.
But still, the bigger efficiency of the electric car would come to be beating this part of this fleet,
yes.
From my point of view.
Yes, yes.
So if we are talking real life, I'm afraid that it will be much more complex.
Mm-hmm.
At this moment, there are no taxes. All the governments are having taxes just and only from combustion engine driven cars.
Yeah.
So
the tax policy, of course, is a very important one. And at the end, when we are in the electric fleet, there will also be taxes for electric cars. But this will also control the prices a little bit because of competition. Today, I just know it from Austria, you can pay on a public charging station in Austria between about 35 cents per kilowatt hour and €1.20. So there's a huge range, and there is not enough competition. When the fleet gets bigger, there will be more competition also on that costs. And the taxes, of course, play a role, but on the other hand, you will not be able, as a provider, to account €1.20 for a kilowatt hour. Nobody will buy that. So there is a certain control effect of the market. But for sure, the taxes will not make it cheaper, for sure.
I should take a guess. It's not even estimation, it's my guess. Now, what will happen in 27 years? I am sure just and only on one aspect. Everything will be much, much more expensive.
Yeah.
So I do believe that in 2050 we will not have cars. And we will not have such huge amount of cars because we don't want to have them.
Mm-hmm.
Because it will be so expensive that we will be somehow forced to use different way of transport.
Yeah, I agree. So never the things really got cheaper, right? But in 2050, there might be other options. And this is my next chapter. So if there is time, I will give a short outlook to autonomous driving cars, about half an hour, if you agree, because this might be an increasing share of business cases that you do not own a car anymore. You just use it. You just use the service of mobility.
If I can just make a note before your slide, there was very fascinating study where people think, everybody believes that people like to share.
Yeah.
They don't want to own something.
People don't want to share.
And the result of the huge study was that they don't share because they want to share.
Yeah.
Because they don't want to own car.
Yeah.
They share because they do not have enough money to share.
That's right.
It totally changes the whole picture.
Yeah, there are different aspects working here. But I will show you. I will show you just more on the technology side what's about digitalization and automation. And this is the second big area where companies invest billions of euros. So really much money goes into that. And I want to show you some status of technology. This automated driving is a vision, right? So there are expectations, a big business here to earn money with this. Also to increase safety, I believe that. I'm not so sure if it reduces traffic, because there might be more vehicles even on the road, if they are robotic vehicles. But anyway, there are challenges. It's complex. I will show you on the next slides. The legislation is not completely clear, so the responsibility is not clear, and there are some ethic questions if a robot, so a machine, hurts people, for example. Anyway, what is the status here? And these driver assistance functions are divided into 5 levels. So SAE levels, or also VDA, so the German Community of Car Manufacturers, agreed to these 5 levels. Assisted is in mass production. This is adaptive cruise control, for example. Partially automated is in mass production. This is a highway pilot, so you can buy this since years. But the red line indicates that the human driver has responsibility. The level 3 system is highly automated. That means that the system takes over responsibility, and the driver can read a newspaper or type text messages. And this is very new. Since beginning of 2022, Mercedes-Benz has a level 3 system in mass production. So they have the homologation, they have the permission to sell a level 3 system. It's a very specific system because it only operates on the highway up to 60 kilometers per hour. Now you might smile, okay, highway 60 kilometers doesn't make sense. No, it's intended to be some kind of traffic jam assist on the highway. When you have in a city a traffic jam, then it operates. And in that situation, you really can take the hands off, you can read a newspaper, and the machine takes over. The next level, level 4, means that the car still has a steering wheel and pedals, but in most cases, it is able to drive autonomously. We do not have level 4 systems in mass production cars. Level 5 means there is no steering wheel, there are no pedals, it's a robot that moves people or moves goods. These level 5 vehicles are not in mass production, but are in commercial use today in the United States and in China. I have some examples I will show you. So these are the different levels, and the big step or the big jump is here to get to level 3 to give the responsibility to the car. This is the big challenge in development. Here are some examples, and when we look at this slide, we see on the upper side of this slide, we don't see car manufacturers. On the upper side, and these are the top companies in that area, several companies that invest billions and that have test cars on the road, and these are not really car manufacturers. So these are IT companies. And here you see the background. The idea is to earn money with customer data, with customer service. And there's a big field of earning money. Of course, there are also car manufacturers. So Tesla, I will talk about Tesla in a minute. Mercedes with the level 3. Volkswagen Moya, they start with the autonomous bus fleet, so a small bus fleet in Hamburg. So also car manufacturer invest increasingly and bring cars into road. And there is some kind of misuse with the terminology. Tesla, for example, called their system autopilot, or they even call it full self-driving mode. But it is still a level 2, perhaps a level 2.5 system. That means the driver has to supervise it, and the driver is responsible. Even if it is called autopilot, it's not an autopilot. So take care with this. When you look in the internet, you find some bad accidents of Teslas because the people did not take care. One example, I have a photo here because nobody was hurt. You find this video, it was in Taiwan. When you look in the internet for Tesla crash Taiwan, you find that because it was filmed by a traffic camera. What happened? A truck rolled over, independent of the Tesla. It rolled over, and the truck was loaded with these breakfast boxes, these Chinese breakfast boxes. And the Tesla came on the highway, and this is filmed by the camera, and the sensors did not identify the truck because the color of the soft top was nearly the same as of the sky. So the contrast was not enough. The Tesla did not see the truck and crashed into the truck. Luckily, nobody was hurt because the Chinese breakfast box is damped. So in that way, Chinese breakfast boxes save lives, right? Anyway, therefore, because nobody was hurt, I have it on my screen. And you can find it in the internet when you look for that. So there are risks, of course, of that technology, and there are different levels. Another story, perhaps very interesting to hear, Waymo. Waymo is seen as the company with the highest experience in that field. It's a Google spin-off. And they operate taxi fleets in United States cities. They do that since years in Phoenix, in Arizona. With a smartphone application, you can call a Waymo. There is no driver, so it's a level 5 system. And it brings it to a destination. And since August this year, they also do it in San Francisco. I have been in San Francisco this year in August, and I have seen them driving around without a driver in the traffic. And you can believe San Francisco traffic is really tough traffic, so not really very controlled traffic. The second company that also operated in San Francisco was GM Cruise. This here. They also got the permission to do this in commercial way as taxi services, but there happened an accident 4 weeks ago, where a car did hit the pedestrian. A manual-driven car did hit the pedestrian. The lady who was hit was pushed on the ground, and the cruise car rolled over the feet. And it did not stop. It did not recognize. It just then drove some meters more and stopped the car at the side. And this was, of course, an error system. The lady did not die, but she was very much injured, very much hurt. And after that event, Cruise did lose their license for that taxi service. Waymo still have it. Cruise did lose the license. So I just want to show there are risks, but there are cars on the road. I have also some Chinese examples. Pony AI and Apollo do in Shanghai and other Chinese cities similar services. Yeah, this is just an example of such a people mover. It's Zoox. Zoox is an Amazon company, and they develop such an autonomous people mover. You see no steering wheel. You sit like in a tramway. You call the vehicle by a smartphone. You get transported in the city. They are not in commercial use yet, but they announced to go into very soon. With this example, I just want to show you these new vehicle concepts. I have also prepared some videos here. So when you, perhaps Pietro can share the slides, you will find that in the internet, where you see very nicely how the systems operate. Besides people transportation, good transportation is an issue. So to transport the pizza in the evening or the purchase from the supermarket. And in general, we have it since years, so the Amazon warehouse robots, right? Or in production or other closed facilities, there is a good potential. But when we do it on public roads, we always have the interaction with the people, and this is challenging. There are some vehicles on the road, like this Starship Tech in Los Angeles. When you look for that, you find very funny videos because this very small vehicle has troubles with pavestones, right? They hang there and cannot move, and the pizza is inside. Nuro is bringing a grocery store purchase in Silicon Valley, in Mountain View. And what we had was a project with the Post. And here I would like to show you a video. It was a project with the Austrian Post, where we built a demonstrator to investigate and to show the potential in real city traffic. It's a very short video. The idea was that the vehicle gets the packages in the post station and then autonomously navigates in the inner city area of Graz, of my city, and brings the packages. And we have restricted the speed due to safety reasons. We also have supervised the system. But we really tested it for 1 week in the inner city of Graz. And we had pedestrians, bicycles, dogs, and cats, and cars, and whatever. Nothing was happened. So it worked. This is the good news. And it was very interesting to see how this system, or what are the requirements on such a system. So we need digital maps. We had highly sophisticated sensors. I will show you on the next slide. To identify the objects, to navigate with GPS system. And at the end, after 1 week, it was a rather successful project. So, and these services, in the meantime, are on public roads, not in Europe, but in United States. Very similar vehicles are driving on public roads. So this is, in the meantime, state-of-the-art in California. Okay, let's jump back. Here, I want to close my talk today with a little bit technique, but more representative technique. Because the most important thing is to identify objects, right? To identify road signs, to identify persons, cars, bicycles. And here, different sensor systems come to use. We have here different types of vision systems. Cameras, we have radar sensors, we have laser sensors. And besides that, we have, of course, the onboard sensors, speed of the car, acceleration, and we have GPS and communication. But regarding the sensors, I would like to show you it on the example of the Waymo system I mentioned before. This is the car that drives autonomously taxi services in San Francisco. And you see, it's not simple, right? We have 29 cameras. We have several laser sensors, far distance and close distance laser sensors. We have radar sensors. We have a high performance computation because all the data have to be computed in real time, right? When the car drives, it must be in real time because otherwise it would be too late to brake, for example. And this, of course, is a very highly sophisticated system. And what I want to show you is some examples of what a sensor sees, so that to get an impression. This is a sensor that we have in mass production cars for brake assist or adaptive cruise control. I just start the video. And you see in the video a filmed scene on the highway. And here you see the car with the sensor, and the car in front is this pink one. And what you see, there are a number of rectangles approaching. Most of them are not relevant. Only a small share of the rectangles, and they are identified in blue color, show other cars, for example. So the radar sensor delivers a good information that there is something and the distance to that, but the signal has to be filtered and the software has to be able to identify if the objects are relevant or are not relevant. So the disturbance grade is relatively high. As a difference to that, a camera system, I will show in the next video, has a much higher quality of object recognition. So give me a second. I show you here a video that was published by Tesla. It was an earlier stage of the development of this full self-driving mode, but I like the video because you see very nice the different objects. So you see here the safety driver. It does nothing, it's only for safety. Can you see here the speed? Here is the navigation route defined, and what is interesting is shown here on the right side. So in green color, you see objects that are relevant for the driving path. In blue color, you see objects that are identified but not relevant, not intersecting the driving path. And in pink and red color, you see traffic signs and road lines. I just want to show you that video. So it's a traffic situation where Tesla drives from Mountain View to another village in Silicon Valley. And the speed is shown in miles per hour. So you have to about double it to have kilometers per hour. And you see this in automated driving mode. In this video, you will not find an error of the system because it was published by Tesla. We have tested it also very comprehensively, and there are always some situations where you have to, bye-bye, good evening, where you have to interact manually because there are dangerous situations. But what you see here very nicely is how the system identifies people, bicycles, cars, how it keeps the distance, how it steers, and it works not bad, I have to say. So it is not a bad system, but it's not 100%. And that is the problem. When you drive 100 kilometers and there is 1 kilometer an error, you might die. So the system has to be reliable and 100%. Otherwise, it would be too dangerous to use it as an autopilot, right? So in that way, I see the Tesla system as a very good driver assistance system, but not yet as a self-driving system. So here I'm more skeptic, I have to say.
For me, I'm very optimistic because we are people and mankind, and people are stupid and mankind is also acting stupidly. So for the last 30 years, I'm quite fascinated by autonomous driving. And for the last 30 years, every single year, was a legal limit or legal risk. So for the last 30 years, every year there were endless discussions that it's not safe enough, etc. And what Tesla proven quite black and white, that people don't care.
Yeah, that's...
People used autopilot as autopilot.
Yeah.
Then they started. Then accident started. People were dying. But all the other people who were driving Tesla, they simply did not care.
Yeah.
They accepted that they will die.
Yeah.
And they just done it.
Yeah, but there is the one difference. If you supervise the system, it is good and it will support you during driving and it will make your driving more safe. When you do not supervise the system, when you sleep or you read a newspaper or you even sit at the rear seat, what happened, you might be killed.
Yeah.
That is the small difference.
It's not like technical or technological aspect.
Yeah, it's a human aspect.
It's a human aspect.
Yeah, I agree.
They start dying, and they simply didn't care.
Yeah.
It was okay.
Yeah.
They will still do it. They will die, but they will still do it.
Yeah.
Fascinating.
Okay, this I wanted to show you. And the last one is the laser sensor, because we hear a lot often about laser sensors. And what I show you here is just a short video sequence from Velodyne. Velodyne is a very well-known supplier of laser sensors. This is a synthetically generated scene. It's different as the Tesla video and the radar sensor video I showed you before. But all the data were produced by this top roof laser scanner. And just I want to show you here is the three-dimensional quality, right? With the laser scanner, we really get a three-dimensional information of the environment in real time, and that of a very high accuracy. Of course, there are also challenges with the laser scanner. It's a light-based system, so there might be reflections, there might be dirt or fog in winter or whatever. But if it works, the quality is very high. And that's the reason why the Waymo, for example, use laser scanner, whereas Waymo use all three: camera, laser, and radar scanner to have redundant system, right? But I just wanted to give you an impression that you have an idea. The laser scanner brings a three-dimensional picture of the environment. Okay, with this, I would like to finish. I think it talked a little bit too long. I'm sorry for that. But yeah, I wanted to show you so many things. And for sure, I'm open for questions. So can I answer some questions? Oh, I just jump up here for the background. Does not work. I just go to the title slide. Okay, here. Some questions, some discussions, please.
I have two questions here. The first one would be a bit question of how people behave when these autonomous cars are surrounded.
Mm-hmm.
For me, it's quite uncomfortable that when I see that there is a driver, I know that this car can be moved. But if the driver is not there, there should be some sign that the car should be.
But what is the car doing, right?
Yeah. Because after it will be straight more dangerous to cross because you don't know from which car will start the ride.
Yeah, that's right. So this is the human-machine interaction, right? I can just tell you, I was in San Francisco this summer, and I saw these autonomous cars on the road, and some people don't like them. And what they do, they took the cones from construction area and put it on the motor hood of the car so that the car stood still. They disabled the car by putting something on the hood, and the car stood still because they don't like it. There were also some protests from taxi drivers, and I have to say that these cars are relatively careful. So they don't go over the legislative boundary conditions. They don't drive faster, they stop when it's red and an end. And with this, they produce sometimes traffic jam. They also had some troubles with software, then there was traffic jam. So some people in San Francisco were really angry with that cars, and they don't like it. So this is one issue, that the social interaction. The second one is that what you meant, when I'm a pedestrian, for example, how can I estimate what is this car doing? And here is a big room for research. I know some companies, they are working on this interaction, where they, for example, build screens on this car in the front, that the screens inform with simple signs what they are doing. Or they project with a laser on the floor so that they start driving or go that. So this is an absolute important area where we will see some new approaches in the future to communicate with a human taxi driver. The taxi driver might show you something or react or look at you, and you see, okay, he has seen me. And here we have to find a new approach for the autonomous car to interact with the humans. Yeah, I agree. Mm-hmm.
And my second question will be have two parts. What is your guess when this technology will be mature for the use in the Europe? And the sub-question of this question is, in Scotland they testing the bus, which is autonomous, and they say that in 2025 they will be able to use it in that way, and there has to be some loophole in legislative that they can do it. So what is, how this works? Where they can do it?
So I think for defined applications like a bus that always drives the same route or the same route, here we will see that in the next 3 years in Europe, in applications. Why? Because we can prepare that. We can apply digital maps, we can prepare sensors even on the road or in the infrastructure that communicate with the bus or that give signals. So the technology is so far that I think it's feasible that in the next 3 years we will have several cities in Europe, small buses as people movers operating. For the very general, everywhere driving autonomous car, I see it very difficult. So not before 2035, whatever, but it's looking into the crystal ball. Why? Because there are so many, so different boundary conditions. We have winter, we have snow, we have ice, we have our historically grown cities in Europe, like Brno city. So I'm in a hotel in the inner city of Brno. It's wonderful, but it's terrible to drive with the car, right? So this is difficult. But for some applications, for specific applications, same as Mercedes did with the highway pilot. Here we will see it. On the highway, Mercedes announced they will go to 120 kilometers per hour, right? So because it's a defined boundary conditions. Here we will see it in the next 3 years, more and more, also in buses, also in private cars, luxury private cars, but not for pressing the button and everywhere it will work. This I don't see here so soon.
Okay, and generally in Europe we will get in 4 or 5 years allowance of car in the highways?
Yeah. So this allowance for the Mercedes is still given in Europe for this system, for this level 3 system. And also the legislative side looks at the experience, what happens. Does it work? Are there problems or not? And I'm an engineer, so I'm optimistic. And I think that it will work for highway and it will come more. It will also contribute to safety because when it works, it should work reliable. So I think, yes, the legislative boundaries will change for that. Also for the buses in predefined areas. Yeah. Mm-hmm.
Thank you.
You're very welcome. Please.
I would like to ask you, I hope that my question will be proper, but it's more for discussion, because today you mentioned some numbers, and also margins, and also natural resources when it comes to Europe, US, China, and so on. I just wonder, I'm a European, I love Europe, and I would love to have that extra margin in Europe, and I hope that Europe won't change into some cheap assembly line. So I just wonder, because from the data you showed today, is that the winner of the game when it comes to economy is China, because when it comes to law, they don't care. When it comes to taxes, they have their own rules. When it comes to comfort of people, it can be the same. You know, when it comes to rules in the cities, it can be the same. They just crossing all the philosophy and values that we have in Europe. So is it really the future that China will economically win this, or do you see some, because you're into the topic, do you see some points for Europe that we will have that extra margin? Because also I wonder when it comes to BMW, Porsche and other car companies, they are selling their technology to China because be part of the Chinese market, it's a huge thing. I'm working for Siemens, so I know something. Also I was in Korea, so when it comes to Hyundai, I saw the reality. So I would love to have some positive vibes.
I want to give you some positive vibes. Regarding margins, what we have today, so I don't look into autonomous driving cars. No, I look on that what is today, and here we have the electric cars. And with the electric cars, we have the problem that some Asian companies, it's just about 5 or 6, control the battery market. This is, for example, CATL, it's a Chinese company, it's LG, Korea, it's Panasonic, Japan, it's BYD, it's Chinese, and some others, Samsung perhaps. So 5, 6 companies have the knowledge to produce battery cells in high quality for automotive industry. And this value creation of the cell production today is mainly in China. They have invested their billions, really high numbers of billions of euros or dollars over the past more than 10 years, and they're really good with that, I have to say. That means that when you buy a BMW or a Volkswagen electric car, the battery cells are from Asia. And this is going to change. The European government, the European politics has seen that this must change. And they support very much production in Europe. So there are big battery plants to be produced in Europe this time, to be built in Europe this time. But, and now comes the but, the first ones who build battery plants in Europe are the Chinese companies and the Korean companies. So CATL, LG, and so on. But it is first, just a second, it's a first step. So to bring this to Europe. The second step is to establish European companies that produce batteries. And here we have some interesting companies, Northvolt, for example, and some others, which are European companies and which try to be competitive to the Asian companies. And here I think that we can do it. So I believe, I'm optimistic that we can do it, that the value creation will be brought back more to Europe to stay competitive here. But I agree, the industry was sleeping in this point, and also the politics was too slow in this point. So we lost a lot here. Now we have to try to keep up or try to accelerate to be competitive. Yeah.
Sorry to be risk assessment man in the middle. We are lost. If we will not change totally battery technology, we can produce as many battery production factories here in Europe as we want. We do not control resources. China controls like 95% of lithium as resource, as chemical substance. And China will not hesitate a second or a millisecond if they will say, wow, we have competition on Europe, what we will do? Europe will not receive 1 gram of lithium because it's our. They control everything, everywhere.
Yeah, I kind of went through the data, so some of the points I got also is the reason why personally I'm voting for hydrogen, even though it's quite challenging, that word challenge, instead of explosive or what was used before. I also went through like patents when it comes to like car manufacturers, and it's amazing. For example, when it comes to Tesla and patents, they have got the less patents on the market, but they're just using the patents of other companies. So I just wonder, because Chinese and Asian cultures, they are very great when it comes to copying stuff. So if
so I agree that with the resources, with the materials, China is the largest producer and processor. So even if the cobalt, for example, is mined in Congo, they process it in China to a large share. Here I agree. But it starts to move a little bit. So
too little, too late.
Too little, too late, but better too late than never, right? And I could believe that sodium-ion batteries, we don't need lithium, right?
Not available in next 10 years for car.
There is a car in mass production today with sodium-ion battery. Yeah, so you find that. It's a small car, and it's a Chinese car, but the technology is here, and they are driving on the road. So I could believe that it will progress further. And when looking at the total economy, what are we doing today? We import oil. So this is also not a good solution for Europe, right? And now we import parts of the battery. Perhaps it's better than import oil. So when we compare that economically.
If I use my pessimistic geopolitical point of view, you are really playing with fire.
Yeah, sure, sure.
And we, as Europe, we are doing bad job.
I'm not sure if we do a bad job, but we slept over.
European car companies are going down, like they are really going down. What France is doing? They are playing additional tax. They plan to use additional taxes for Chinese battery cars that are supposed to be imported, and they are just only trying to slow down tide, basically.
Yeah, but it's a good point. This has a greenhouse gas impact background, because the idea of that, what you said, is to certify products in terms of their CO2 footprint. And you remember the diagram where I showed the electricity impact in China, for example, or another country with high impact. If you produce something there, the CO2 footprint is much higher than you would produce in France, for example, or in Norway. And what is discussed here is to create a tax that relates to that CO2 footprint. And this, of course, could make it more difficult for imports from high CO2 countries, and this could protect the European economy.